Our universe should not exist as we know it. That is the startling truth behind 22 cosmic coincidences, strange alignments in nature that have no right to be so perfect. The physicist Freeman Dyson once remarked that the universe, in some sense, must have known we were coming. This journey reveals why he might be right, showing you a cosmos that appears suspiciously tailored for life. You will discover why the moon perfectly covers the sun during an eclipse, and how a number governing the atom holds the key to all chemistry. Are these eerie symmetries just lucky flukes, or is there a deeper design at work? By the end, you will see the cosmos in an entirely new light, questioning the very nature of reality. What does it mean that we live in a universe that seems to expect us? That perfect alignment in our sky is a gift of time. The moon is slowly, inexorably moving away from our world. In the distant future, it will appear too small in our sky to ever completely cover the sun again. Total solar eclipses will become a memory of Earth's past. So why do we exist in this narrow sliver of cosmic time, this precise moment when the numbers align so perfectly? It feels less like a random event and more like a performance staged for an audience. This leads us to a second, even more fundamental coincidence, one that operates on the smallest of scales. The strength of the force that holds our very atoms together seems equally fine-tuned. This is the force of electromagnetism, governed by a mysterious number known as the fine structure constant. If this number were even slightly different, the universe would be a barren, lifeless void. If it were a little bit smaller, atoms could not bond together to form molecules. The simple act of two hydrogen atoms joining would be impossible, meaning stars would never ignite and chemistry itself would fail to exist. There would be no water, no DNA, no planets. Yet if this constant were just a tiny bit larger, the fierce heat of stellar furnaces would prevent the formation of any complex atoms heavier than hydrogen. Stars would burn out in a cosmic flash, leaving no time for life to ever emerge. This number, this seemingly arbitrary value, sits in a razor-thin zone that allows for a rich and complex cosmos. It is a dial set with impossible precision, a fundamental rule of reality that quietly permits our existence. This delicate balance of forces within the atom finds a breathtaking echo on the grand scale of our solar system. Earth itself occupies a cosmic sweet spot, a narrow band of orbital real estate where life is not just possible but can flourish. We are not too close to our star, where oceans would boil away, and not too far, where they would remain permanently frozen. This is the habitable zone, a region so perfectly tuned for liquid water that it feels less like a random location and more like a reserved seat for life. Our planet's stability is another layer of this incredible fortune. A steady, nearly circular orbit ensures we receive a consistent amount of solar energy, preventing wild temperature swings that would shatter any chance for complex biology. Even our large moon plays a vital role, its gravitational pull acting as a steadying hand that prevents Earth's tilt from wobbling chaotically over time. Without this lunar anchor, our climate would veer between extreme ice ages and searing heat, making the long, stable development of life nearly impossible. Every condition appears meticulously arranged, as if our world were placed here with intention. This fine-tuning on a planetary scale compels us to look even deeper, to the very laws of physics that govern the entire cosmos. What other impossibly precise numbers had to be set correctly for our universe to even be possible? The very laws that allow Earth to flourish in its cosmic cradle extend down to the most fundamental level of reality. This brings us to a number so profound that physicists have been baffled by it for generations. It is the fine structure constant, a value of approximately 1 over 137. This is not a number with units like meters or seconds. It is a pure, dimensionless constant that dictates the strength of the electromagnetic force, the very glue that holds atoms together and allows them to interact. If you were to imagine the universe having a control panel, this would be one of its most sensitive dials. Turn it just a fraction one way, and the force becomes too weak. Protons and electrons could not form stable bonds, meaning atoms would never link up to create molecules. The universe would be a barren soup of isolated hydrogen, with no chemistry, no water, and no building blocks for life. Turn the dial just a fraction the other way, and the force becomes too strong. Stars would fuse their hydrogen fuel into heavier elements so violently and rapidly that they would burn out in a cosmic flash, leaving no time for planets to form or life to evolve. The fact that this number is so perfectly poised in a razor-thin window for complexity is what led the Nobel laureate Richard Feynman to call it one of the greatest damn mysteries of physics. Why 1 over 137? Why not 1 over 136 or 1 over 138? The value seems utterly arbitrary, a random selection from an infinite number of possibilities, yet it is perfectly calibrated for a universe that can eventually ask questions about itself. This enigma forces us to confront a staggering possibility. Are the fundamental laws of our cosmos a random cosmic lottery ticket, or do they point to a deeper, hidden layer of order we have yet to uncover? The mystery of the fine structure constant is dwarfed by an even greater cosmic puzzle, one that governs the fate of the entire universe. This is the enigma of the cosmological constant, the number that describes the strength of dark energy. When Einstein first introduced this concept into his equations, he envisioned it as a kind of cosmic repulsion to balance the pull of gravity, keeping the universe static. He would later call it his greatest blunder, but modern science has revealed he was right for a completely different reason. We now know the universe is not static, but its expansion is accelerating, driven by a mysterious force we call dark energy. The cosmological constant is our best measure of its strength. The problem is one of unimaginable scale. Our best theories of the quantum world predict that empty space should be teeming with a violent, seething energy. This vacuum energy should give the cosmological constant a value so astronomically huge that it defies comprehension. If these theories were correct, the repulsive force of dark energy would have been so powerful that it would have torn the universe apart in the first fraction of a second after the Big Bang. Galaxies, stars, and planets would never have had a chance to form. The cosmos would be a thin, featureless, and ever-expanding void. Yet when we look out into the cosmos, we measure the cosmological constant to be incredibly small, almost zero. It is not zero, which is why the expansion is accelerating, but it is 120 orders of magnitude smaller than what our physics predicts. To put that number into perspective, it is like comparing the size of a single proton to the size of the entire observable universe. This is not just a small error. It is the most staggering mismatch between theory and observation in the entire history of science. Why is this force so inexplicably weak? It appears to be exquisitely fine-tuned. If it were even slightly stronger, the universe would have blown itself apart before any structure could coalesce. If it were slightly weaker, the force of gravity would have pulled everything back together in a catastrophic big crunch long before life could evolve. We exist because this number, for reasons we cannot explain, is balanced on a razor's edge. This cosmological constant problem forces us to confront a profound question. Does this precise calibration point to a universe that was somehow designed for complexity? Or are we simply the lucky inhabitants of one universe among an infinite multiverse, a cosmic lottery ticket where all the numbers just happen to come up right? The answer to that question may lie in the very first moments of everything, in the initial conditions that set this entire cosmic story in motion. This impossible fine-tuning of the cosmological constant is mirrored by the very shape of our reality. The geometry of our universe is perfectly flat. This is not flat like a tabletop, but a precise geometric flatness on the grandest of scales, meaning the fabric of space itself does not curve back on itself in a closed cosmos nor bow outward in an open one. For this to be true, the initial density of the universe, just moments after the Big Bang, had to be balanced with unimaginable precision against the outward force of expansion. The required accuracy is staggering, fine-tuned to within 1 part in 10 to the power of 60. To grasp that number, imagine balancing a pencil on its tip so perfectly that it would still be standing a billion years later. The slightest deviation, a fraction more density, and gravity would have quickly won, pulling all matter back into a catastrophic big crunch. A fraction less, and the universe would have expanded so rapidly that matter would have flown apart before gravity could ever pull it together into the first stars and galaxies. Our cosmos would be a cold, dark, and empty void. To resolve this flatness problem, scientists proposed the theory of cosmic inflation, a period of unimaginably rapid expansion in the universe's first fleeting moments that stretched any initial curvature into the flatness we observe today. Yet this only pushes the mystery one step further back. What caused inflation to begin, and why did it end with the exact conditions needed for our universe to persist? As physicist Alan Guth has pointed out, this incredible precision seems essential for creating a long-lived, stable universe where life can eventually arise. The initial conditions appear to have been set with a perfect, almost unnatural hand. This profound coincidence forces us to ask what or who was holding that pencil. Are we looking at the random starting point of a single cosmos? Or does this razor's edge beginning hint at a deeper law, a mechanism that naturally births universes with the right parameters for life? To find an answer, we must peer back even further into the very first moments of time itself. This staggering imbalance of forces is written into the very fabric of reality. The force of electromagnetism that binds atoms is about 10 to the power of 36 times stronger than the force of gravity that sculpts galaxies. To even begin to comprehend that number, try to lift a paperclip with a small magnet. The magnet's electromagnetic force easily overcomes the gravitational pull of the entire Earth. Now imagine if that ratio were not so extreme. If gravity were even slightly stronger relative to electromagnetism, the universe would be a very dark and short-lived place. Stars would be crushed under their own weight, collapsing in on themselves so fiercely that they would burn through their nuclear fuel in mere millions of years, a cosmic blink too short for planets to form or life to emerge. Conversely, if electromagnetism were even a little stronger compared to gravity, its repulsive power would prevent cosmic dust clouds from ever collapsing to form stars in the first place. The gentle tug of gravity would be utterly powerless to pull matter together. The night sky would be empty, with no stellar furnaces to forge the carbon, oxygen, and iron that make up our bodies. This precise, incomprehensibly large ratio is what allows for both the existence of massive, long-lived stars and the stable, intricate chemistry of life. It creates a universe where gravity can build the grand stages of galaxies, while electromagnetism handles the intricate backstage work of building complex molecules. No fundamental theory predicts why this number should be so perfectly suited for our existence. It simply is. we are left to wonder if this is merely one more entry in a long list of lucky breaks, or a silent, fundamental declaration that this cosmos was always meant to build something more than just dust and empty space. This precise tuning of forces extends into the very heart of every atom you are made of. The proton and the electron, the fundamental positive and negative charges that define matter, possess a mass ratio that is just as critical as it is mysterious. A proton is roughly 1,836 times heavier than an electron. This is not a trivial detail. This specific, lopsided balance is what allows for the stable architecture of the atomic world. If the electron were significantly heavier, its chaotic quantum behavior would destabilize the orderly shells surrounding the atomic nucleus, preventing atoms from ever linking together into molecules. The chemical bonds that form water, DNA, and every substance you can touch would simply fail to materialize. Conversely, if the proton were even a little lighter, the fierce nuclear furnaces inside stars would sputter and fail. The processes that fuse hydrogen into helium, the very reactions that power every star in the sky, would be catastrophically altered. Stars would either fail to ignite entirely or would burn through their fuel in a frantic flash, drastically changing the universe's elemental makeup. There would be no long-lived stars to warm planets, and no cosmic factories to forge the carbon and oxygen that are essential for life. This one number, 1,836, acts as a silent, universal regulator. Its value seems arbitrarily fixed, yet it permits a cosmos rich with chemistry and light. This has led some physicists to a profound, if controversial, line of thought known as the anthropic principle. The idea is that we can observe this perfect balance precisely because we exist to observe it. In a universe where these constants were even slightly different, no one would ever be around to wonder why. The very fact that we are here to measure this ratio implies that our universe, against incomprehensible odds, had to be this way. This atomic fine-tuning is not an isolated miracle. It is one thread in a vast, interconnected tapestry, a series of cosmic conditions that collectively build a bridge from the subatomic void to the grand structural symmetries of the universe itself. The delicate balance within the atom finds its ultimate expression in the fiery hearts of stars. Deep within these cosmic forges, the universe faced a critical bottleneck in its ability to create the very stuff of life. The element carbon, the essential backbone of every living thing on Earth, should have been incredibly rare. Its creation relies on a stunningly precise nuclear reaction. In the 1950s, the astronomer Fred Hoyle calculated that for carbon to form in any significant quantity, it would require a highly specific and unlikely shortcut. He predicted that the carbon-12 nucleus must possess a particular, excited energy state, a resonance that would allow it to form efficiently when three helium nuclei collide. Without this exact resonance, the helium nuclei would simply bounce off one another, and carbon would fail to accumulate. The chance of such a perfect energy level existing seemed astronomically low, yet Hoyle was so confident in his calculations that he convinced nuclear physicists to run experiments to look for it. To their astonishment, they found it. The carbon-12 nucleus did indeed have that exact resonant energy level, right where Hoyle said it must be. Without this one specific quantum mechanical doorway, the universe would be devoid of carbon-based life. There would be no trees, no animals, and no humans to ponder the stars. Hoyle himself, who was not a religious man, saw this as clear evidence of a superintellectual influence, a manipulation of physics itself. This carbon resonance is not just a lucky break. It is a fundamental feature of reality that appears suspiciously convenient. It is as if the laws of nuclear physics were pre-arranged to guarantee the production of a key ingredient for biology. This profound stellar coincidence forces us to look beyond the stars and back to our own planet, to examine the other biological prerequisites that had to fall perfectly into place for our existence to become possible. This same cosmic generosity that gives us carbon also provides its crucial partner, oxygen. The life-giving fusion processes inside stars do not stop at carbon-12. That carbon nucleus can fuse with another helium nucleus to form oxygen-16, the very element that makes water and the air we breathe possible. But here, the universe faced another razor's edge decision. The oxygen-16 nucleus itself possesses a specific energy level, a resonant state. If this oxygen resonance were just a little bit higher, nearly all of the precious carbon forged in the stars would have been greedily converted into oxygen. A universe with abundant oxygen might sound hospitable, but without sufficient carbon, the complex organic chemistry that life depends on would be impossible. There would be no carbon-based molecules, no DNA, no proteins. Yet, if this oxygen resonance were slightly lower, the opposite would occur. The reaction from carbon to oxygen would be far less efficient, leaving the universe rich in carbon but desperately poor in oxygen. Without ample oxygen, there would be no water, the universal solvent of life, and no ozone layer to shield fragile biology from the sun's harsh radiation. The fact that both the carbon and the oxygen energy levels are perfectly poised, creating a universe with a plentiful supply of both elements, seems like a miraculous compromise. It is a nuclear balancing act of breathtaking precision. Astrophysicists who run the calculations find this tuning far too exact to be easily dismissed as a series of fortunate accidents. It suggests a cosmos whose fundamental laws are inherently biased toward creating the conditions for biochemistry. This intricate dance of element formation, where two of life's most vital ingredients are produced in perfect harmony, forces us to look beyond the stars. We must now consider the planetary environments where these elements finally assemble into the intricate, self-sustaining systems we call life. This planetary shield is not a static barrier, but a dynamic, living force. Deep within Earth, a swirling ocean of molten iron generates a powerful magnetic field that extends thousands of miles into space, creating an invisible protective bubble around our world. This magnetosphere acts as a cosmic deflector shield, bending the torrent of charged particles streaming from the sun, the solar wind, away from our fragile atmosphere. Without this constant, active defense, our planet would be stripped bare. The story of Mars serves as a stark and sobering reminder of what happens when this shield fails. Mars once had a thicker atmosphere and flowing water, but as its smaller core cooled and its magnetic field faded, the solar wind slowly scoured away its air, leaving it the cold, radiation-blasted desert we see today. Our own field is a gift of planetary scale and composition. Earth is large enough to maintain a hot, molten core for billions of years, and its rapid rotation helps churn that liquid metal into a self-sustaining dynamo. If our planet were just a little smaller or rotated more slowly, this protective generator could have sputtered and died long ago. The constant barrage of radiation would have eroded our atmosphere, boiled away our oceans, and bombarded the surface with enough energy to shatter DNA and prevent the rise of anything more complex than the hardiest microbes. This is not a distant threat. Even now, slight fluctuations in the magnetic field create weak spots, like the South Atlantic anomaly, allowing radiation to dip closer to the surface and offering a glimpse of a world without its full protection. That we exist on a planet that has maintained this perfect defensive barrier for over 3 billion years, precisely spanning the entire history of life, feels like more than mere fortune. It is as if the very ground beneath our feet is actively conspiring to keep us safe, setting the stage for the next incredible coincidence that hangs quite literally in the air we breathe. This protective magnetic field works in concert with another, equally vital atmospheric filter, one we experience with every breath we take. Our sky is transparent to the very light that gives us life. Sunlight streams through the air, bathing the surface in the precise wavelengths that plants use for photosynthesis, the engine that powers nearly every ecosystem on the planet. Yet, this same atmosphere is brilliantly opaque to the sun's most dangerous emissions. A thin, diffuse layer of ozone gas high above our heads acts as a global sunscreen, absorbing the vast majority of incoming ultraviolet radiation. Without this shield, the intense UV rays would penetrate shallow water and soil, shattering the complex molecules that form the foundation of life. DNA itself would be relentlessly damaged, making the evolution of anything beyond the simplest single-celled organisms a near impossibility. This perfect balance of clarity and opacity is not a random feature of any planet. It is the result of a specific atmospheric composition, a mix of gases that has been carefully curated over billions of years. The oxygen that makes up much of our ozone layer is itself a product of life, pumped into the air by ancient cyanobacteria in a planetary transformation known as the Great Oxidation Event. The atmosphere and the biosphere are locked in a delicate, self-reinforcing dance. If our air were slightly less transparent, too much visible light would be reflected or absorbed, plunging the world into a perpetual gloom and starving plants of the energy they need. If it were slightly more transparent, the unfiltered ultraviolet radiation would sterilize the land. We inhabit a world that has somehow calibrated its own windows to let in the good light and keep out the bad, a global greenhouse with perfect settings. This exquisite tuning of our immediate environment points toward an even larger pattern, a synchronization that extends beyond our planet's conditions to the very timing of our existence within the cosmos. The air we breathe and the light we see are gifts of a planet perfectly tuned for life, but our own existence is timed with an even grander cosmic clock. We live in what astronomers call a golden age of observability. Look up at the night sky and you can see other galaxies, the faint afterglow of the Big Bang, and the vast history of the cosmos written in light. This is not a permanent feature of the universe. It is a fleeting window, and we are here at the perfect moment to look through it. The universe is expanding at an accelerating rate, driven by that mysterious dark energy. In a few billion years, this expansion will have carried all other galaxies so far away that their light will no longer be able to reach us. The night sky for any future civilization will be utterly black and empty beyond our own Milky Way. All evidence of other galaxies, and therefore the key clues to an expanding universe and a Big Bang, will have vanished forever. Further into the future, stars will burn out, and the cosmos will become a cold, dark, and lonely place. We exist in this narrow sliver of time, a brief epoch when the universe is still transparent, still lit, and still telling its story. The philosopher Brandon Carter framed this as a temporal version of the anthropic principle. It argues that observers like us can only find ourselves in an era when observation is possible. We could not have arisen in the universe's first fiery moments, nor in its distant, frozen demise. We are here now because now is the only time we could be. This is more than just a logical tautology. It feels like a profound synchronization. Our consciousness has awakened at the one moment in the entire lifespan of the cosmos when we can look back 14 billion years and deduce our own origins. The fact that our timeline as a species overlaps so perfectly with the universe's timeline of observability seems impossibly convenient. Are we merely lucky to be born in this cosmic spring, or does our act of observation itself complete some deeper, more mysterious circuit of the universe, a cosmos that has become aware of itself at the very moment it was possible to do so? Our planet's dance through space is choreographed by a single, crucial number. Earth is tilted on its axis by precisely 23.5 degrees. This is not a random angle. It is the master switch for our seasons, the engine of our planet's climatic rhythm. Without this tilt, the world would be a far more monotonous place. The equator would be perpetually scorched while the poles languished in permanent, deep freeze. There would be no gentle spring, no warm summer, no crisp autumn, no cold winter. The middle latitudes, the very regions where human civilization and much of Earth's biodiversity has flourished, would experience only minor temperature fluctuations throughout the year. This lack of seasonal change would drastically reduce environmental diversity. There would be no driving force for the mass migrations of animals, no trigger for hibernation or breeding cycles, and far less pressure for life to adapt and specialize. The incredible biological richness we see around us might never have developed, yet this tilt is a delicate instrument. If it were significantly greater, say 45 degrees, the seasons would swing violently between extremes. Summers would be blistering infernos, and winters would be devastating ice ages, creating a world of relentless stress for any emerging ecosystem. If the tilt were much smaller, the global climate would slide into a stagnant uniformity, with weather patterns stagnating and biodiversity likely stunted. What is truly remarkable is the stability of this tilt. Our large moon, with its steadying gravitational pull, acts as a counterweight, preventing Earth's axis from wobbling chaotically over thousands of years. Without this lunar anchor, our tilt could vary wildly, turning our stable climate into a chaotic roller coaster. Planetary scientists note that this precise, stable tilt is unusual. Mars, for example, with its 2 small moons, has a tilt that varies wildly over time, contributing to its dramatic climate shifts. This perfect 23.5-degree tilt, held in place by a giant moon, feels like yet another dial set with incredible precision. It created the dynamic, ever-changing world that pushed life to evolve, adapt, and become more complex. This intricate celestial arrangement does not end at our atmosphere. The fine-tuning extends far beyond, into the quiet, protected neighborhood our solar system calls home within the vast Milky Way galaxy. Our perfect galactic address is a quiet suburban street in a vast and often violent metropolis. The Milky Way galaxy is a sprawling disk of 100 billion stars, but not all neighborhoods are created equal. We orbit our sun within what astronomers call the Galactic Habitable Zone, a narrow, life-friendly ring situated between the chaotic inner city and the sparse, impoverished outskirts. This specific location is a masterstroke of cosmic real estate. Had our solar system formed closer to the galactic center, we would be subjected to a constant, deadly barrage. The density of stars is so immense that nearby supernova explosions would be frequent, sterilizing planets with blasts of intense radiation. The gravitational pull from the supermassive black hole at the galaxy's heart would also wreak havoc, destabilizing planetary orbits and unleashing torrents of X-rays. Life would be snuffed out before it could even begin. Yet, if we were located much farther out in the galactic suburbs, we would face a different kind of poverty. The outer regions of the galaxy are composed primarily of primordial hydrogen and helium, lacking the heavier elements necessary to form rocky planets like Earth. There would be no iron for a planetary core, no silicon for continents, and no oxygen for water. Our solar system resides in the sweet spot, far enough from the dangerous core to enjoy a stable, quiet existence for billions of years, yet close enough to the inner galactic regions to be enriched with the metallic ashes of long-dead stars. This cosmic recycling of elements means our planet and our very bodies are built from stardust forged in those violent inner regions, but delivered to a safe and stable location for construction to begin. Astronomers estimate that only a small percentage of the stars in the Milky Way enjoy such a privileged position. This spatial luck forces a profound shift in perspective. The Copernican principle taught us we do not occupy a central, special place in the universe, yet here we are, living in a remarkably special place within our own galaxy. This perfect placement challenges our notions of mediocrity and begs the question of whether such fine-tuned environments are rare flukes or hidden prerequisites for a cosmos that inevitably gives rise to observers. This same cosmic generosity that gave us a perfect galactic home is written into the universe's oldest light. The cosmic microwave background is a fossilized echo of the Big Bang, a faint glow that fills every corner of the sky. Its temperature is almost perfectly uniform, a steady 2.7 degrees above absolute zero no matter which direction we look. The precision of this sameness is staggering, varying by only 1 part in 100,000. This incredible homogeneity was the universe's essential starting condition. It meant that matter and energy were distributed with near-perfect smoothness, allowing gravity to pull on the cosmos evenly. Without this initial balance, the universe would have been a chaotic patchwork from the very beginning. Overdense regions would have collapsed into monstrous black holes almost instantly, while underdense regions would have flown apart into utter emptiness. There would have been no gentle, gradual collapse of gas clouds to form the first stars and galaxies. The seeds for our cosmic home would never have been sown. Yet, this perfect smoothness is itself a profound mystery. A universe born in the fire of the Big Bang had no time for its far-flung regions to communicate and equalize their temperature. It is as if a room were instantly filled with air that was the exact same temperature in every corner without ever having been mixed. To resolve this, scientists proposed the theory of inflation, a moment of hyper-fast expansion that stretched a tiny, uniform patch of space into our entire observable cosmos. But this only deepens the enigma. What set up that perfectly smooth, infinitesimally small patch in the first place? The physicist George Smoot, who led the team that first mapped the tiny fluctuations in this background, described it as looking at the face of God. Those minuscule ripples, those 1 part in 100,000 variations, were the blueprints for everything we see today. They were the slight gravitational seeds around which all galaxies, including our own Milky Way, would eventually form. The fact that the background is so exquisitely smooth, yet imprinted with just the right amount of imperfection, feels like a cosmic recipe followed with impossible care. The universe had to be uniform enough to avoid immediate chaos, but varied enough to eventually build complexity. This ancient light is more than a relic. It is a signature of a cosmos that began with a level of fine-tuning that defies random chance, setting the stage for the very forces that would sculpt its eventual evolution. Deep within the heart of every atom, a silent titan holds the universe together. This is the strong nuclear force, the most powerful fundamental force in nature. Its sole purpose is to overcome the immense repulsion between positively charged protons, gluing them shoulder to shoulder with neutrons to form the atomic nucleus. Without this force, the universe would be nothing but a featureless cloud of hydrogen, a single, simple element adrift in the void. The very existence of the world around you, from the oxygen you breathe to the iron in your blood, depends on this force being calibrated with impossible precision. If the strong force were even slightly more powerful, the universe would have faced a catastrophic nuclear greed in its earliest moments. protons would have fused together with reckless abandon, greedily converting nearly all of the primordial hydrogen into helium in the first few minutes after the Big Bang. While this might sound harmless, it would have been a death sentence for the future cosmos. Stars like our Sun rely on a slow, steady burn of hydrogen fuel, a process that lasts for billions of years and provides the stable environment necessary for life to evolve on orbiting planets. If all the hydrogen were gone, stars would have no long-term fuel source. They would either fail to ignite at all or would burn out in a frantic, short-lived flash, leaving no time for planets to cool, for water to form, or for biology to begin its patient work. Yet, if the strong force were just a fraction weaker, the opposite and equally bleak scenario would unfold. It would be too feeble to bind protons together against their fierce electromagnetic repulsion. The fusion of even a single proton with another would become impossible. The universe would be permanently stuck with hydrogen. No helium would form in the early universe, and no heavier elements would ever be forged in the hearts of stars. There would be no carbon, no nitrogen, no oxygen. The entire periodic table, with all its glorious diversity, would simply not exist. We are here because the strong force operates with Goldilocks perfection. It is powerful enough to build a rich tapestry of elements, yet restrained enough to leave a plentiful supply of hydrogen fuel for trillions of stars to shine for eons. Particle physicists openly admit that the strength of this force is not something we can derive from any deeper theory. It is a number that must be measured, a fundamental input to our reality that appears to be set to exactly the right value. This is not a matter of simple adjustment. It is a fundamental parameter that defines the very possibility of a complex cosmos. Why does this force possess this specific, life-permitting intensity? Is it just one more cosmic lottery win in a long series of lucky numbers? Or does its perfect positioning point toward an even deeper layer of quantum mystery, a hidden architecture where all these forces are woven together into a single, elegant tapestry of law? The universe has a pulse, a steady rhythm of expansion measured by a single, crucial number known as the Hubble Constant. This value tells us how fast galaxies are receding from one another, and by running that cosmic film backward, we can calculate the age of everything. The answer it gives is 13.8 billion years. This is not an arbitrary span of time. It is a duration that feels suspiciously perfect. This cosmic timeline is long enough for first-generation stars to live out their violent lives, exploding as supernova to seed the cosmos with the heavy elements for rocky planets. It then provides a second, even longer peaceful interlude for those planets to cool, for oceans to form, and for the patient, intricate dance of chemical evolution to eventually give rise to life. The expansion rate set by the Hubble constant is the master clock governing this entire process. If that rate were even slightly faster, the initial pull of matter would have been overcome too quickly. Galaxies would never have condensed from the primordial gas, and stars would never have ignited. The universe would be a cold, diffuse, and structureless haze. Yet if the expansion were just a little slower, gravity would have gained the upper hand long ago. The cosmos would have reversed its growth, collapsing back in on itself in a catastrophic big crunch after only a few billion years, far too soon for any but the most primitive life to possibly emerge. We exist in a universe that has expanded at a rate exquisitely balanced between these two catastrophes. It is a rate that provided just enough time for carbon to be forged, for solar systems to assemble, and for intelligence to awaken. Cosmologists today debate the precise value of the Hubble constant, with different measurement techniques yielding slightly different results. But this ongoing scientific tension only highlights the profound nature of the mystery. However you measure it, the expansion rate sits within a razor-thin window that permits a long, fruitful, and complex cosmic story. Why does the universe's clock tick at this specific, life-allowing pace? This temporal alignment is one of the most profound coincidences of all, a synchronization of cosmic history with biological possibility that urges us to consider the final, most intimate layer of this fine-tuning, the biological constants written into life itself. This biological clock, the rate at which DNA mutates, ticks with the same life-permitting precision as the cosmic constants. Every living thing on Earth is shaped by this hidden rhythm, a delicate balance between chaos and order written into our very genes. If the mutation rate were too high, the genetic code would become a garbled mess with each new generation. The intricate instructions for building a complex organism would be riddled with errors, making stable life impossible. Yet if the rate were too low, evolution would grind to a halt. There would be no new variations, no raw material for natural selection to work with. Life would remain forever simple, static, and unable to adapt to a changing planet. Earth seems to have found the perfect setting. Our planet's protective magnetic field and thick atmosphere act as a shield, filtering out just enough of the cosmic and solar radiation that can damage DNA. This creates a stable molecular environment where mutations can occur at a pace that is both creative and controlled. It is a rate that allows for innovation, for the slow, patient experimentation that led from the first single-celled organisms to the staggering diversity of the animal kingdom, and ultimately to us. Biologists see this not as a frozen number, but as a dynamic equilibrium, a gift of our planetary conditions. The very constants of physics that govern radiation and molecular stability seem to conspire with our world's environment to enable this evolutionary engine. Is this optimal mutation rate yet another dial, set not just in the laws of physics, but in the specific, safe harbor Earth provides? It ties the grandest cosmic forces directly to the emergence of intelligence, forcing a final, profound question. What is the ultimate product of all this fine-tuning? Is the universe's true goal not just life, but a mind to witness its own existence? This same quantum generosity that grants us starlight operates on a principle that defies common sense. Deep within the heart of our sun, a seemingly impossible act occurs millions of times every second. Atomic nuclei, each carrying a powerful positive charge, should violently repel one another like two north poles of a magnet being forced together. The electromagnetic force between them creates a formidable energy barrier, a hill too steep for them to climb under normal stellar conditions, yet they fuse. They achieve this miracle through a quantum loophole known as tunneling. Think of it not as climbing the barrier, but as vanishing from one side and instantly reappearing on the other, as if digging a secret tunnel through an impassable mountain. This is not magic, it is a fundamental feature of our reality, a consequence of the wave-like nature of particles at the smallest scales. Without this single quantum quirk, the core of every star would be a dark, cold, and inert place. The universe would be a vast collection of hydrogen clouds with no nuclear fires to ignite, no light to warm planets, and no elements to build them. The very existence of stars hinges on this subatomic cheat code. The efficiency of this tunneling process is exquisitely sensitive to the universe's fundamental settings. It depends on precise values like Planck's constant, which governs the quantum world's fuzziness, and the specific masses of protons and electrons. If Planck's constant were even slightly larger, making quantum uncertainty more pronounced, protons would tunnel too easily and too often. Stars would burn through their hydrogen fuel in a frantic, short-lived frenzy, exploding long before planetary systems could stabilize. Conversely, if this constant were a tiny bit smaller, tightening the rules of the quantum realm, the probability of tunneling would plummet. Protons would rarely, if ever, overcome their mutual repulsion. Stellar cores would remain dormant, and the cosmos would be forever dark. The physicist George Gamow was among the first to realize that this quantum tunneling was not just a curious footnote, but the very engine of the stars. Why do the laws of physics include such a convenient escape clause? This subatomic convenience feels less like a random rule and more like a carefully crafted provision for energy production. It forges a direct link between the bizarre, probabilistic world of the very small and the brilliant, life-sustaining reality of the very large, strongly hinting that the microscopic and macroscopic realms are threads in a single, unified tapestry of law. That quantum generosity has a dark twin, a perfect mirror image that should have erased our existence before it even began. For every particle of matter the universe created, it should have created an equal and opposite particle of antimatter. When matter and antimatter meet, they annihilate each other in a flash of pure energy, leaving nothing behind. In a perfectly symmetrical cosmos, this would have been the fate of everything. All the particles and all the antiparticles would have found each other in the first chaotic second, cancelling the entire universe back into a featureless sea of radiation. Yet here we are, living in a world made entirely of matter. Every star, every planet, and every one of us is the remnant of a staggering cosmic crime, a primordial theft where matter somehow won. This victory hinged on an almost imperceptible flaw in the universe's perfect symmetry, a process known as baryogenesis. In the first fleeting instance after the Big Bang, for every 1 billion antiparticles, there were 1,000,000,001 particles of matter. That one part in a billion asymmetry was enough. When the inevitable annihilation finished, that one extra particle in every billion was left over, the sole survivor of a near-total destruction. This tiny residue is all the material that would ever exist, the entire substance of our cosmic home. The precision of this imbalance is as critical as it is mysterious. If that asymmetry had been any smaller, say 1 part in a trillion, the annihilation would have been far more complete. The leftover matter would have been too sparse, too thinly spread across the expanding cosmos for gravity to ever pull it together into galaxies and stars. The universe would be a dark, diffuse, and radiation-dominated void, utterly silent and lifeless. Yet if the asymmetry had been slightly larger, the universe would have been born with far more matter. The increased density would have led to a dramatically different cosmos, one where matter collapsed into monstrous black holes with terrifying speed, or where the expansion was halted by the sheer weight of substance, pulling everything back into a fiery big crunch long before life could stir. We exist because the initial theft of matter was calibrated to a razor's edge, leaving just enough debris to build a rich and structured cosmos, but not so much that it collapsed under its own weight. This overwhelming dominance of matter is one of the most profound puzzles in all of physics. Our most fundamental theories demand a perfect balance, yet reality presents us with a lopsided universe. This points to unknown laws operating at energies we can scarcely comprehend, physics that inherently favors existence over oblivion. The fact that we are here at all is proof that the universe, from its very first moment, was subtly biased toward creating something rather than nothing. These cosmic threads weave a tapestry of staggering scale and design. When astronomers map the universe in 3 dimensions, they do not find a random scattering of galaxies. Instead, they reveal an intricate cosmic web, a vast architecture of brilliant filaments and walls made of galaxy clusters, all separated by unimaginably large, dark, and nearly empty voids. This is the large-scale structure of our universe, and it is the direct result of those tiny, 1 part in 100,000 ripples in the primordial cosmic microwave background. Those minuscule seeds of density, stretched by cosmic inflation and then amplified by gravity over billions of years, grew into the grand design we see today. The specific pattern of this web, the thickness of its filaments and the scale of its voids, was not preordained. It hinges on the exact properties of dark matter, the invisible cosmic scaffolding that gravity sculpts, and on the precise parameters of that initial inflationary burst. This is where the tuning becomes critical. If dark matter had been even slightly more interactive, or if the inflationary expansion had proceeded at a different rate, the cosmic web would look utterly alien. The universe could have become far too lumpy, with matter collapsing into enormous, isolated supergalaxies so dense that stellar collisions would be frequent and planetary systems unstable. The resulting radiation would likely sterilize any emerging worlds. Alternatively, if the initial conditions had been even smoother, the cosmos might have failed to clump together at all. The gentle tug of gravity would have been insufficient to overcome the expansion, leaving behind a universe that was a near-perfect, featureless haze of thinly spread gas. There would be no galaxies, no stars, and no planets. Our existence depends on a universe that clustered into structure, but did so with a specific, balanced rhythm. Cosmologists run immense computer simulations, tweaking the properties of dark matter and the rules of inflation, trying to recreate the exact web we observe. The fact that only a very narrow set of initial conditions produces a universe that looks like ours is telling. This architectural fine-tuning of the cosmos itself suggests that the blueprint for reality was optimized to build complex environments where life could take root. It invites a staggering thought. If our universe's large-scale structure is just one possible outcome from a near-infinite menu of possibilities, does this point toward a multiverse, a vast cosmic ensemble where every possible set of physical laws is played out in some other domain? We may simply be the lucky ones, living in the one universe whose cosmic web was perfectly woven for galaxies like ours to form, and for stories like ours to be told. This final cosmic coincidence is written into the very backbone of your DNA. Phosphorus is the unsung hero of biology, the essential spark in the molecule ATP that powers every cell in your body, and the crucial link in the double helix ladder that holds your genetic code. Yet for all its vital importance, phosphorus is strangely scarce in the cosmos. Unlike carbon or oxygen, which are forged in abundance within many stars, phosphorus requires a very specific and violent kind of stellar death. It is primarily created in the fury of type Roman II supernova, the colossal explosions of massive stars. The amount of phosphorus that escapes such an explosion and gets seeded into interstellar space is not a given. It hinges on the precise nuclear physics occurring in that stellar inferno. If the conditions within those supernovae were even slightly different, if the complex chain of nuclear reactions tilted just a little, the universe could have been left with a devastating phosphorus poverty. Astrobiologists now see this scarcity as a potential great filter, a universal bottleneck that could prevent countless worlds from ever crossing the threshold into complex life. Without a robust supply of phosphorus, the elegant machinery of life simply seizes up. Adenosine triphosphate, or ATP, could not form to store and transfer energy within cells. The structural integrity of DNA and RNA would crumble. The very system for storing and reading genetic information would fail at its foundation. So why does our planet and our very biology seem to have just enough? It appears we are the beneficiaries of a specific style of stellar suicide, one that tuned its explosive yield to produce this critical element in exactly the quantities needed. This is not a matter of simple stellar chemistry. It is a profound link between the cataclysmic death of giant stars light years away and the metabolic fire crackling within each of your cells. The phosphorus in your body right now was once part of a star that lived and died violently, and its journey to you required a universe whose fundamental laws allowed for that one specific element to be produced in perfect proportion. From the precise strength of gravity to the quantum quirks inside atoms, from the flat geometry of the cosmos to the elemental gift of a long-dead star, these 22 coincidences weave together into a single, inescapable narrative. They tell the story of a universe that seems to have been expecting us, a cosmos meticulously prepared from its first instant to become a home for minds that could look back and finally begin to understand the miracle of their own existence. These 22 threads are not separate. They weave together into a single, breathtaking tapestry. The precise strength of the strong nuclear force allows stars to forge carbon, and that carbon's specific resonance permits its survival long enough to be swept up by a planet orbiting within the galactic habitable zone. That planet's large moon stabilizes its tilt, creating seasons, while its molten iron core generates a magnetic field that protects an atmosphere transparent to sunlight yet opaque to lethal radiation. This atmosphere, in turn, filters just enough cosmic rays to maintain the perfect mutation rate for DNA to evolve. Tug on one of these threads, and the entire intricate fabric of our reality begins to unravel. Alter the fine structure constant by a fraction, and stellar chemistry fails, leaving no carbon for life. Shift the cosmological constant minutely, and the universe either tears itself apart or collapses, leaving no time for planets to form. Each coincidence is a single domino in an impossibly long chain. The sheer number of these interdependent, finely balanced conditions creates a picture of staggering consistency. It is a universe that does not merely permit life as a random afterthought, but one that appears fundamentally rigged for it, from the quantum realm to the cosmic web. This cumulative evidence forces a profound debate among physicists and philosophers. Some see the hand of a cosmic designer, a superintelligence that set the dials. Others propose a vast multiverse, an infinite ensemble of universes, each with different physical constants, and we simply inhabit one of the rare, life-friendly ones. A third possibility is that we are missing a deeper, unifying theory, one that would naturally explain why these constants must have the values they do. Yet the sheer weight of these alignments makes the idea of pure, undirected chance seem increasingly untenable. We are left with a cosmos that feels exceptionally, almost suspiciously, hospitable. This synthesis is more than just a list of lucky breaks. It is the foundation for a final, humbling realization about our own role in this grand narrative, and what it truly means to be a conscious part of such a finely tuned existence. From the subatomic dance of quantum tunneling to the galactic architecture of the cosmic web, each of these 22 alignments forms a single, coherent story. They reveal a cosmos that is not a chaotic accident, but a realm of breathtaking order and precision, improbably suited for the emergence of life and mind. The sheer accumulation of these facts defies simple explanations of luck, forcing us to confront the profound questions of chance, necessity, and perhaps even purpose. We are not merely inhabitants of this universe, we are a product of its most fundamental and finely tuned laws. As Carl Sagan so beautifully observed, the cosmos is within us. We are made of star stuff. Every atom of oxygen we breathe, every particle of iron in our blood, was forged in the heart of a long-vanished star. Our existence is a conversation between the quantum and the cosmic, a dialogue written into the constants of nature. Let this journey inspire you to look up at the night sky with a renewed sense of wonder. See it not as a distant void, but as a shared heritage, a home that has been preparing for our arrival for billions of years. We invite you to share your own thoughts on these staggering mysteries in the comments below. What do you believe these coincidences reveal about our universe? For more deep dives into the enigmas of space, be sure to subscribe. Remember, in a cosmos filled with so many perfect alignments, our enduring curiosity remains the most powerful tool for discovery we possess.